this idea of the mean value theorem. And the green sheet, hopefully you picked up, has a bunch of homeworks on it. This is a little bit of a, maybe a little longer of a unit. And we're titling it the applications of derivatives. So at this point, you should be really good at taking the derivative of basically anything that comes your way, like at all, even the most exotic functions. Like I said, I challenge you to give a function to your friend in this class that they can't differentiate, right? It should be almost, but what can we do with them? Clearly, we can find slopes and tangent lines and all of that, but we'd like to think about like what else can we do? And this unit answers that in spades. And by application of the derivative, we definitely mean to the real world, that's for sure, but also inside of mathematics. So the mean value theorem is an example of something we'll do here with derivatives and have a discussion today about that. The extreme value theorem is also another theorem we'll talk about. We'll talk about the first and second derivative tests and some curve sketching, how the derivative affects how we look at graphs. We'll talk about two important applications that every student loves in calculus class: optimization and related rates, too. And this is what's pictured here, actually. You'll come across, a couple of you I know who took AB. Anyone who's ever taken a calculus class in America has done this classic problem, and you will too, with the coffee maker and coffee filter here, where they're like, there's water draining out of a coffee filter and into a coffee pot. It's an interesting problem. Anyway, but it's so classic, everyone does it, that we were like, we had to make fun of it in our photo a little bit. So we're taking some data. And did we work the pool noodles into that one? Oh, they're in the background. Okay, that's good. Okay, they're at least there. All right. We didn't know how to work them in exactly, but yes, I'll.
What happens like when we used to like drive by like the signs?
Yeah. What?
They would, like, say, like,
It just hasn't happened at all for my calculus course. Yeah. So, well, we try to switch things up a little bit, you know?
Oh, yeah, I see.
Try to do something different for each. So we'd like to talk about the mean value theorem today, and this is the mean value theorem. I'll just put it right up here. It's the thing that appeared almost exactly in the wording I'm using here on the bottom of this activity as you got to the last problem, right? Here's the hypothesis. Yes, it has to, both of these things are met, hopefully. Continuous over the closed interval, differentiable over the open interval. And if that's true, then we have that there must be some value in the interval where the instantaneous rate of change is equal to the average rate of change on that interval. So I have it both in kind of math up here and in words down below. Okay? I'm going to leave that up there while we go over the answers to your worksheet here. Okay? So just as a reference, I mean that's the thing we're thinking about. So let's just run through these and see how you guys did. So just listen as we can handle this. We'll go kind of quick through it. So get ready. You can be called off. Okay. So I'll say, we've done this before, right? I'll say your name, you'll give the answer, and then everyone else will say agree if they agree. Okay. So Katie, what did you say for one? That first one says from the graph C is approximately. What did you say? 5.3-ish. What do you guys say? Do you guys say agree? I mean, that's one I guess you don't say agree to, right? You say, yeah, maybe, kind of, yeah. Ish. Everyone say ish, okay. Rosa, what'd you say about, is it differentiable in the open interval? Agree? What about on the closed interval, Josh? Is it continuous?
Yes.
Agree? Okay. Number 2, give both values if you can, approximately. What do you think their mark is? Say it one more time. And 5.2.2 he said, and 5.8. You guys agree roughly-ish? Okay. Patricio, what about, is it differentiable in the open interval? Yeah. Continuous on the closed interval, Amy? What did you say there?
Yes.
Okay. And agreed? Sorry, did we agree with Patricia? Sorry. I need to practice this too. Number 3. Now we got a new function g pictured down below. Is g differentiable on the open interval? Tran, what did you say there? Number 3, Ron. It's all good. It's all good.
Oh no.
Okay. And is G continuous, Zachary, which there on the closed interval? Where are you? It's number 3. Is G continuous on the closed interval 1 through 5? 1 to 5? Yeah? Agree? Okay. And then, do we want to say why there's no value? Someone will volunteer to say why. I mean, one reason we could say that there's like, because the mean value theorem says so, but we don't know the mean value theorem, at least at the time of the writing of this, of doing of this question. Yeah, you could say something about it's obviously the cusp is an issue. You want to say more, Jonathan? Yeah, all the slopes are greater than the average slope, or on the other side, less than, right? Yeah, so I mean, you kind of go from, you can feel the violation of the mean value theorem actually as you compute slopes going from left to right, can't you? The slopes are like 1, 1.2, 1.2, 1.3, 1.4, 1.5, like then 1,000, and then so it's like pretty smooth, right? You get like these nice increasing slopes, and then suddenly negative 1,000. Negative 999, right? Like, and never are they, whatever this, what is the average rate change there? 1/4 or something, right? Never are they, or 1/2, I guess. Never are they that low. Good. Moving smartly along. Number 4. Part for what's the value of C? Did you say there? What did you say, Kathy B? 3. Okay. And is G differentiable on the open interval, Albert?
Yes.
And is G continuous on the closed interval, Judah?
Yes.
Yes? Agree. Okay. Number 5, is H differentiable on the open interval, Jennifer? This is our new function, this crazy piecewise one. On the open interval, agree? Yes? On the open interval, I think we're okay. Charlotte? What about, is it continuous on the closed interval? No. Agree. And again, what do we want to say about, do we want to say anything, can someone volunteer to say something? Why, maybe from an intuitive standpoint, why is that not working there? Why don't we have a C value? We don't reach every slope. You want to say it another way? I mean, I don't have anything I'm looking for necessarily. There you go. That's a great observation too. Yeah, I think just like intuitively, you're like, yeah, this isn't going to work, right? I'm definitely not even on the search. I think it's just like, no, there's definitely not a C value. Good. Number 6, Ian, is it differentiable on the open interval? Yes, agree. Joe. Joel. Someday I'm going to say your name correctly. Continuous on the closed interval?
No.
And Peter, could you tell me what you think the value of C is there?
6.
So incredibly, there is a value still, though, that we think works. Did you guys get about 6? Something in there? Answers may vary, but approximately that. Number 7, Jonathan, tell me, is it differentiable on the open interval, this crazy function?
Yes.
What else do we have to say here? Someone want to explain why H is continuous, actually, on the closed interval? They're telling you it is, so it might at first seem like that's not true, but yeah. Yeah, the endpoint is 5, so it can do whatever it wants, says Judah. Yeah, keep in mind the definition of continuity for an endpoint is a little different than it is for interior points, isn't it? You remember that? Like the one-sided limit has to agree. Okay, all that. Christina, what about can you take this? Number 8, the hypothesis, which ones were the hypothesis and the conclusion true for the mean value theorem?
I said 1, 2, 4, and 5.
That's what I said. We should be friends. Okay, Max. What did you say for hypothesis and conclusion are both not true?
3.
3? I gotta look at these again here. 3, yeah, right, because the hypothesis is false. And 6? Right, I mean, we're just looking for one that you said no to, at least on one of the 2 questions. And 3 and 6, I think, are those. The conclusion is true, but not the hypothesis. Vivesh, did you come up with one of those? I think you're. Which one? Which one? Which one? We're looking for one where the conclusion is true. That is, we found a c-value, and yet it didn't actually meet the hypothesis of this theorem. That is, we said like yes and no, or no and no, or something like that to the question. You have like a question mark after your statement. Are you sure?
Number 6.
Okay. Do you guys agree? Let's give it some validation. Okay. Yeah, number 6, because it fails the hypothesis to meet the hypothesis. Do you agree? Because I think you answered yes and no, and then yet we still have a C, don't we? All right, and then let me ask you one more too that's not on there. Are there any where the hypothesis is true and the conclusion is false? Hopefully not, if this really is the mean value theorem, right? Hopefully we don't have any. Obviously, if the hypothesis is met, then hopefully the conclusion follows, right? Good. So the mean value theorem is then stated, on number 8. It was there, and here it is as well. It also just kind of makes intuitive sense, doesn't it? Let me show you the picture one more time, though you probably don't need it after having done this, but we'll have it up here just so you see it. So we have the slope of the secant. We're looking for a place where the tangent has the same slope on that curve, and the mean value theorem, if we have those two things met, then supposedly we're guaranteed a value where this happens. Intuitively, just with pictures, it seems to make sense, right? By the way, how did you actually go looking for that place? You drew your secant line, and then how did you look for that place? You took your, you kind of did a little translation, yeah? Up and down, maybe, okay. I mean, no. I mean, I think if you move it left, you might be, well, I mean, you have a line, I guess. You have a whole line, so you're right. Yeah. I was thinking about that segment in the picture, but you're right. Okay. Good. Makes me also think of the following application of this theorem. I don't think you can be fined or ticketed for this, but theoretically, they have every mathematical right to ticket you on the ICC, or I'm from Pennsylvania, so the Pennsylvania Turnpike, if you clock in and clock out at certain times, like if you did 100 miles in an hour, they should be able to ticket you, even though they never observed you.
Yeah.
They theoretically should be able to, mathematically, right?
They do have that
In some places. I think they're maybe not legally allowed to do that yet in here, and in some states maybe it is okay. They certainly have every mathematical right to charge you, right? Because your average speed was 100 miles an hour, say. Can we guarantee there was a time, at least one time, when you were going 100 miles an hour? I think we can, right? So unless you were to claim, you might try to claim, well, I was going 60 miles an hour the whole time. I just drove in a discontinuous manner, or there was a moment where I transported from here to here, and that's why. Or I was driving in a non-differentiable manner, officer, or something like that. I don't think that'll fly, but I think you drive in a continuous and differentiable manner at all times. Nick, is that a question?
Are there cameras on the highway?
Yeah, on the ICC there are cameras that take, so they know how to charge you. Well, like I said, theoretically they could charge you, I think. I mean, they have the information. They have very accurate data on how fast you went, right? Yeah, I don't know. That's a good question. Why are they allowed to use speed cameras that calculate a very, very small average rate of change and not very big average rates of change? I don't know. Here's a picture I'm going to share with you here. This is a bridge, f of b, it says, I want to make sure you see what it says here, because it's said a little differently than what we said, how we said it. F of b minus f of a equals f prime of c times b minus a. Is that the same? Is that a formulation of the mean value theorem? It is. We just have like the b minus a has been multiplied over here. It's actually a formulation I really like that will serve us well in an interesting way in the second half of this course. Yeah, where is that? Do you know? Anyone know? It's in Beijing. Just a few blocks south of Tiananmen Square. So if you go to China, forget all the temples and the historical significance of Tiananmen Square. Like, tell your tour guide or your parents, whoever you're with, this is I need to go to the mean value theorem bridge. David, isn't that great? I mean, what culture to elevate this mathematical truth? Literally above us. It's great. I love it. Huh? All right. So, we hopefully have an intuitive understanding of the mean value theorem. We actually didn't provide a proof here today, but let's talk about it in the context of different problems that could be asked. You okay? Okay. First of all, it's not worth very much discussion in guaranteeing that there is such a value here, but let's just say it real quick. Why can I even guarantee that there is a value of x named c on the interval 0 to 2 that satisfies the mean value theorem? Is this x squared continuous on the closed interval 0 to 2? Yeah, in fact, more than that. It's continuous everywhere. And is it differentiable on the open interval 0 to 2? Yes, and more than that. It's differentiable everywhere. So moving on, can I now ask you to actually find that value? Let's do it, right? So what's required in doing that? Try, give it a try. Actually, work your way into that problem a little bit. We don't know where it is. We're trying to find it. So, help me out here. What are you actually physically doing right now on your paper? What calculation are you making? I mean, once you understand the question, there's actually not a lot of really difficult math to do here. But how do you formulate this? What's your computation, Josh? What are you actually calculating? Let's come back together here. You guys are having a great conversation about this, so I like it.
I used the 2 points of 0, 0, and 2, 4 to find the slope of the secant.
Okay.
And I set that equal to f prime of c. That turned into...
So what is the slope of the secant?
The slope of the secant is 2.
Okay. And then say it again. What did you do?
I set that equal to f prime of c, which is 2 times c.
Yeah. So f prime of c is 2 times c, and we want that to be equal to 2. And the algebra, like I said, is not super hard here. So we get c equals 1. We drew that picture before we knew what it was. Otherwise, we would have made it really accurately right here. Yeah? Okay? So that's how this feels. Now, this is the easiest possible problem I could give you. Could it be harder? Absolutely. Let's do one that's a little bit trickier. What's with the Spanish? There's an f of x available to us right now on the worksheet on numbers 1 and 2. If you look at that problem, I'd like to actually find, you estimated it? I'd actually like to find it. Let's actually do it. Now, it's kind of messy, so we might need the calculator. On the interval 3 to 7, is that the one we were using? Or is that me introducing the interval? It is 3 to 7 on the first problem. Notice how I'm doing it too. You're welcome to use this kind of technique. You could put it in Y1, and then you could actually do this calculation on your home screen, right? That's a good question. If you had a curve like this, say,
Yeah.
what's the average rate of change on this interval? Something common that usually.
Yeah.
What's the average of the two instantaneous? What's those 2 points? It works with the that works on other intervals. What did you get for the average rate of change on the interval 3 to 7? Is it exactly a half? If it's something that's not so nice, I think it does come out to exactly a half here. So that's great. I think we can move on, and we have 1/2. If it comes out to something not nice, though, you may want to store the value. Do you know how to do that on your calculator? Or actually, I mean, you could even put this in when you need it in your calculator, but store it maybe in a letter or something so you can use the full value later. So then what are you doing to find that value? What's next? Yeah, find the derivative of our function f, and then what? Set it equal to 0.5, but that's going to be a little messy. What kind of function is it, the derivative of f? F prime will be quadratic equals some number 0.5, so you'll have a quadratic that's not very nice looking though. So you can use the quadratic formula, or we're on the calculator, so how about you just graph that and look for the intersections with the line 0.5, or do something. You have a calculator, right? So so I have the original function in y1, and I haven't actually turned it off. You know how to turn off the function in your calculator? And then I have y2, that's where I put my derivative. It's just the power rule, so I just did it by hand instead of using nderiv or something. I just actually put it in there. And then in y3, I put 0.5. So this is my strategy here, is I'm going to graph the derivative function and 0.5, and I'm going to look for where they're equal, right? That's my strategy. That's what you said too. So, now use your calculator skills to do that. Find the intersection. Does anyone have it yet? No. What'd you get? Okay, this is 2.47. What's this one? 5.527. Well, something. Wait, what is it? I want to make sure that someone else says it.
I got
5.52. Let me give you one more decimal place for AP sake. 8. Okay. AP would accept 5.527 or 5.528. Either truncate or round at the third decimal place. Okay. So why am I actually not reporting 2 point whatever? Yeah. All right. Homework 2 is actually what's going to said at the beginning. Homework 2 is the mean value theorem. That's not due until Monday. Okay? The only thing due tomorrow is you're going to get review books. Okay.
The current leaders are Miss Gaffney, Mr. Beach, and Miss
Take our test tomorrow.
Bringing you tomorrow. Also, all of us Are